Hello everyone, welcome to Reactify Labs. Today, let's talk about Apache Cassandra. Cassandra. Hmm. Okay, what is Cassandra? Cassandra is a NoSQL database. That's what we know about it, right? So, yeah, that's what it is. I do not have any real life example or analogy to give you for this. So, yeah, without wasting time, let's move to discuss the structure that we are going to follow today. So, we will start with the introduction. Okay. After that, we will move to the architecture of Cassandra. Then we will see the data model. After that, we will see consistency, how consistency is addressed in Cassandra. Next, we will see data distribution. Okay. After that, we will see replication mechanism because it's a distributed database. So it must be having some replication mechanism, right? So replication mechanism. Next, we will see fault tolerance in Cassandra. After that, we will talk about the advantages of using Cassandra and challenges associated with it. Okay. So yeah, that's what we are going to do today. Then let's start with the introduction. Okay. Introduction. So Apache Cassandra is a distributed NoSQL database, right? It's a NoSQL database and it's distributed, designed for handling large amounts of data across many commodity servers without any single point of failure. Okay. It's a distributed NoSQL database designed for handling large amounts of data. Handling large amounts of data across many commodity servers. Across many commodity servers without any single point of failure. Without any single point of failure. It provides high availability and scalability. It provides high availability and scalability through its distributed architecture and tunable consistency levels. Okay. So what are the keywords here? First is it's distributed, right? And it's a NoSQL, right? And it distributes the data, handles data across many commodity servers without any single point of failure. So if there is no single point of failure, we can deduce from here that it does not follow a master slave architecture, right? So what does it follow? Let's study more and then we will find out. Okay. Next, let's talk about the architecture. Architecture. So its architecture is distributed and decentralized. Okay. So first is distributed and decentralized. Okay. Cassandra operates in a peer-to-peer network where all nodes are equal and there is no single point of failure, right? So if you have not watched my other video, I don't remember which video it was, but I have discussed about this master slave replication, master replication and peer-to-peer replication. So this one is peer-to-peer, right? So there are different nodes and data is replicated across each node. And Cassandra operates in peer-to-peer network. So all nodes are equal and there is no single point of failure. Each node in the cluster can handle read and write requests independently. Okay. Data is distributed across nodes using a consistent hashing algorithm, which ensures that data is evenly spread across the cluster. Okay. Next is it's a ring-based architecture. Ring-based architecture. So Cassandra uses a ring-based architecture where each node is assigned a range of data based on its token range. The token range determines which data the node is responsible for. Each node in the ring is responsible for a specific range of data. When a write request is made, it is directed to the appropriate node based on the token range. Okay. Next is replication. Next is replication. So data is replicated across multiple nodes based on a configured replication factor. For example, a replication factor of 3 means that each piece of data is stored on 3 different nodes. Cassandra supports several replication strategies, including a simple strategy like for a single data center and network topology strategy for multiple data centers. Okay. Let's see the data model of Cassandra. So it follows a column family model. Column family. So Cassandra uses a column family data model, which is similar to tables in relational databases. Each table has rows and columns, but columns are not fixed and can be dynamically added. Columns are grouped into column families. Each column is a key value pair where key is the column name and the value is the data. Okay. So basically it's like this. So it will be similar to this, what do you call it? Relational, as I mentioned. It's similar. It looks like relational database, but the columns don't need to have single value like relational database or multiple values only. It can have a key value store as well. Okay, and it belongs to a family of data model called column family. Okay, so columns are very dynamic here, very flexible. Okay, columns are grouped into column families. Okay, as I told you, columns, different columns. Let's say okay, let me draw it. So this is one row, another row. So it's possible, right, like that this row, okay, this cell has like this row, this column, and it can have, let's say, multiple columns. Okay, and each column can have its own columns. Okay, so uh, basically Cassandra gives too much flexibility to the columns. Okay, that's why it's called a column family model. Okay, so in conclusion, Cassandra is referred to as a column family data model because it organizes data into column families where each row can have a unique and flexible set of columns rather than rigid fixed schema, as in this relational databases. Okay, so next is rows and keys. Rows and keys. So each row is identified by a primary key, which consists of a partition key and optionally clustering columns. The partition key determines the node responsible for the data, while clustering columns define the order of rows within a partition. Partition key determines the distribution of data across nodes. Rows with the same partition key are stored together on the same node. And clustering columns define the order of data within a partition. They help in sorting and querying data efficiently. Okay. Next, let's talk about consistency. Consistency. So, what is the consistency level in Cassandra? Consistency levels. So, Cassandra allows configuring consistency levels for read and write operations. Consistency levels determine how many replicas need to respond to an operation before it is considered successful. Okay, so there are different examples of consistency levels. For example, 1, it means a response from a single replica is sufficient to say that okay, yes, this operation is successful, this write operation is successful, and it can be considered consistent, right? Another is quorum. I have made a separate video on quorum. You can watch it if you have not watched it already. So it means a majority of replicas must respond. Okay, there is another level which is all. So all the nodes must respond before write can be committed. Okay, and there is one called local quorum. So a majority of replicas in the local data center must respond. So it does not need to do remote procedure calls over the internet. Okay, so yeah, that's the difference between local quorum and quorum. And tunable consistency. Tunable consistency. So Cassandra provides tunable consistency, allowing users to balance between consistency and availability based on their application needs. Higher consistency levels improve data accuracy but may impact availability. So this is what it does. Depending on how available you want or how consistent you want. So for example, if you want your data to be strongly consistent, but you can compromise on availability, you can maybe go with all or a quorum. But if you want it to be compromisable on consistency, but you want very high availability, then maybe you can go with you can go with one or local quorum. Okay. So this is what is meant by tunable consistency. Okay. Next, let's see data distribution and querying. Data distribution and querying. So data is partitioned across nodes using a hash function. Actually, first one, let's talk about partitioning. In this, data is partitioned across nodes using a hash function on partition key. This ensures even distribution of data and load across the cluster. Each node is responsible for a range of tokens and data is distributed based on these token ranges. We talked about this before as well. Okay. Next comes secondary indexes. Secondary indexes. So Cassandra supports secondary indexes to enable efficient querying on non-primary key columns. However, secondary indexes are not always efficient for high cardinality data. And next is materialized views. Materialized views. So materialized views provide a way to create pre-computed, denormalized views of data for efficient querying. They help in optimizing read performance by maintaining data in a specific format. Okay. Next, let's talk about replication mechanisms. Replication mechanisms. Okay. First one is read repair. During read operations, Cassandra checks for discrepancies between replicas and repairs inconsistencies in the background. This helps in maintaining data consistency across replicas. And second is anti-entropy repair. Anti-entropy repair. So anti-entropy repair operations are run periodically or manually to ensure that all replicas have consistent data. This involves comparing and synchronizing data across replicas. So you might want to ask here, what is anti-entropy? Why the name anti-entropy? This is because, let's see. So in a distributed system, we know there are multiple nodes. Okay. Let's assume this is a distributed system having different nodes. Okay. And these different nodes are at different locations. So it's possible that sometimes when some write happened here, and actually this is a peer-to-peer architecture, right? So in peer-to-peer architecture, what happens? Every node takes a write, every node gives a read, right? So every node is a master node in itself. So a write will happen at every node, and it is very much possible that, let's say, a write which happened to this node, it propagated here, but it could not reach these two. Okay. Similarly, some write which happened here could not reach some of the nodes. Okay. Like it could not reach these four nodes. So over time, what happens is the data which is present in these nodes gets diverged, right? So diverged means it gets entropy. Entropy means randomness. If you remember your thermodynamics or equilibrium chapter from class 11th or 12th, there we had studied entropy, right? It is the same entropy. Entropy means randomness. Okay. That the nature tends to go towards a higher entropy means there can be, it will always be a more random. Everything will be more scattered. For example, your room, it's not organized all the time, right? You have to do work, or you have to make an effort to keep your room organized, right? But disorganized, it happens on its own. You don't need to make any effort for disorganizing it, right? So that's what entropy is. So everything in this universe goes towards higher entropy. Entropy means randomness, disorder. So similarly, these nodes also go towards disorder. Okay. this node will diverge, this node will diverge. Since a write is there on every node and failures can happen, there may be inconsistencies in the data present in each node. That's where entropy comes. And anti-entropy means periodically what happens is all nodes will sync data, and since all nodes will sync data, it means the entropy will be reversed, okay, or stopped. This is why it's called anti-entropy. So every time the room becomes disorganized, what happens is the nodes gather together and let's organize the room. Okay, this is what it is. Every time your room becomes disorganized, you clean it. Every weekend you clean it, or let's say every 3 days you clean your room. That's what you do there. You are doing anti-entropy repair. That's what database anti-entropy is. Okay, so this again I would like to reiterate, as I told you in one of the other videos as well, that everything in computer science is taken from real world. So if you see or feel that anything, any word, any terminology is something which you know about in real world, try to relate it with in the computer science also. Okay, actually when you hear it about in this computer science or distributed systems or system design or anything related to computer science, try to relate it with real world, and I assure you, you will understand it better and you will never forget it. I am pretty sure you will never forget what anti-entropy repair is now. Okay, and if you liked this analogy, please give me a like. Okay, comment would be much more appreciated, but a like works. Okay, let's move forward. Fault tolerance. Fault tolerance. So if a node fails, okay, let's say first thing is failover. Failover is related to redundancy. If a node fails, Cassandra automatically redirects requests to other replicas. This ensures high availability and fault tolerance. When a node is temporarily unavailable, other nodes store hints about writes that the unavailable node missed. These hints are replayed to the node once it recovers. And next is again same as anti-entropy repair. Because if multiple nodes can sync on whether their data is synchronized or not, can meet up to synchronize their data, it's not a different case when let's say this node's one data is different from this node's one data, and this node's one data is something and this node does not have any data. So it's the same thing, right? Again, when they will synchronize to update their data, this node will give its all data to this node and update it. Okay, it will tell it that, okay, see, this is how you have to be, right? So that's why anti-entropy repair works here also. Anti-entropy repair operations compare and synchronize data across nodes to fix inconsistencies and ensure data accuracy. Okay, so let's take a real life example. Imagine a library which has multiple copies of each book distributed across several shelves. Okay, each shelf has a specific range of books. Okay, and is responsible for a subset of the library's collection. Correct? So there are different shelves in the library. Each shelf has some different collection of books, and let's say these shelves have the replicas. Okay, this have the replica, this have the replica, and this have the replica. Okay, so when you check out a book, it's recorded in the library's catalog. If a shelf is busy or unavailable, other shelves can help you find the book, right? Ensuring you can still borrow it, right? If the book is not available in one shelf, you can borrow it from the other shelf, right? So the library periodically checks the inventory across all shelves to ensure that each shelf has the correct number of books and missing books are replaced or fixed. So this is also another example of how Cassandra updates its nodes. Okay, not very similar or accurate, but yeah, this is how you can do. As library keeps updating its catalog, Cassandra keeps updating its nodes. Okay, so now let's talk about advantages of Cassandra. Okay, advantages of Cassandra. So first one is scalability. It easily scales horizontally by adding more nodes, distributing data and load evenly across the cluster, right? Because as I told you, it's a peer-to-peer architecture. Everyone is a master. You can add as many nodes as possible, and that's why it's horizontally scalable. Okay. Next is high availability. High availability. It provides high availability with no single point of failure and automatic failover mechanism. Again, the same thing. Distributed architecture, multiple nodes. Even if one node fails, others can serve you, right? And along with this, the tunable consistency that we studied, right? We can configure our consistency and availability. Next is again tunable consistency. So it allows configuration of consistency levels to balance between consistency and availability based on the needs of the application. Then if it's so sophisticated, then there must be some challenges associated with Cassandra, right? First one is complexity. Because again, I'll say the more sophisticated a system is, the more easy it's making your life, the more challenges it come with. So it must be more complex. So the distributed nature of Cassandra can make deployment and management complex, requiring careful tuning and configuration. Next is eventual consistency. Eventual consistency. The eventual consistency model can lead to temporary inconsistencies, which may impact applications requiring strong consistency guarantees. Let's say your application requires strong consistency, but you tune your consistency level to, let's say, to focus on high availability. Then the consistency might get compromised, right? Next is secondary index performance. Secondary index performance. Secondary indexes can have performance limitations, especially with high cardinality data and large data sets, right? This is a very common thing in databases. If you as much indexing as you do, it impacts your performance. Okay, even primary index impacts the performance of the database if you do too much indexing, or even if you do like single indexing, but you try to find something, a query like less than some value, right? Then these kinds of queries are bound to be slow with indexing as compared to non-indexed data. Okay, so yeah, that's all there was about Cassandra. Now in the interviews, if you are asked to draw in a system and you say that I'm using Cassandra here, and the interviewer asks why Cassandra, then you can talk about this. You can talk about a lot of things now, rather than only saying because it's a NoSQL database and it's scalable, it can be horizontally scaled. You have more things to talk about it now. Okay, so yeah, that's all there was in this video. Thank you for watching. Please remember to like, share and subscribe. I will see you in the next one.